theory session on compiler. And is it visible now? I see.
Yes.
Okay.
Yes, it is visible.
Okay. Students, we have last week given an overview of the compilation process, the different phases that a compiler needs to go through, needs to process the program through. And we have seen that the first phase in that is a lexical analyzer. Just to recap, a lexical analyzer is a program, or we'll see as it is an automaton, which takes the program which is written as a sequence of characters and scans them from left to right and keeps on grouping them appropriately into token classes which the language has defined. And as you all are very aware of several languages, the typical such token classes or typical such lexical classes, or we say the entities of the program, include predefined keywords. There could be operators and other special symbol like plus, minus. I think somebody is unmuted. Kindly mute yourself. Thank you. There are different operator symbols. There are special symbols like curly brace, parenthesis, semicolon, colon, and so on. There could be variety of user-defined symbols like identifiers used as names of different entities like functions, like variables, and so on. There could be literals of different types, string literals, character literals, integer constant literal, floating point literal, and so on. So there could be a variety of such different lexical classes or lexical token types into which these characters will have to be grouped. And our whole focus in this current module will be to understand this lexical analysis process. Now, what we'll see in the process is the way this program, this lexical analyzer is written. Certainly, you can always take the whole specification of what are the different lexical token groups and what are the allowed characters and so on, and actually write a program by hand for lexical analysis. Naturally, in early days, that is what people had to do. But subsequently, as it emerged, the complexity of these lexical items became quite large. I mean, you have quite a large number of token classes. You have quite complex definitions for some of them. The languages are having all varied kinds of wide token types. So it becomes very, very difficult to write this lexical analyzer program by hand. At the same time, right advances in the automata theory, you all have done flat, I suppose, formal language and automata theory, has told us that it is actually not required to write this lexical analyzer program by hand from scratch. What we can do, we can write a very compact specification in a different language, for which we will study the language Flex or the system Flex. And it's kind of a language which is very close to the regular expressions that you have studied in flat. And then using the Flex system, we can actually get the lexical analyzer generated. So we are talking about a very interesting thing. We are talking about actually developing a phase of the compiler for which we do not actually write the whole program by hand. Rather, we write kind of a specification and pieces of this program in that specification, and then kind of compile it, but compile it from that specification into a C or C++ program, which is your lexical analyzer. And that system is called Flex. So in this module, we will study both of these and master both of these, that what is lexical analysis and what is this lexical analyzer generator system called Flex. Accordingly, this will be the broad discussions. We'll have an outline of lexical analysis just to understand, and I will not go in very details about this, because much of it we'll see refers to ideas that you have already learned well in the flat course. So I'll just put pointers to that, and then we'll go more depth into the Flex specification, the lexical analyzer generator system, and talk about different advances and variations of that, and how does it really take part in the overall phases of the compiler. So that's what you're embarking into. Now, if we look at the lexical analysis algorithm, then what we are saying is we are processing the characters in the program in the sequence. So it's taking it as a linear sequence of characters from left to right. And we keep on processing and putting them in the same lexical token till we reach a point when we decide that we have already found the lexem, or the character description of a specific token type, be it an operator, be it a keyword, be it a literal, be it an identifier, be it a special symbol, whatever. So what we will try to do is to use the definition of every token class. And as you all have been aware since you have started learning programming languages, and very specifically the PDS course you did, which was common for all of you, where you saw that there are different definitions given for every token class. You are told what is an integer constant, you are told what is an identifier, you're told what are operators, and so on. So everything is specified according to English specification rules. Now, if you look at them carefully, as we will find that these specifications are actually amenable to, or actually are, regular expressions. You all know regular expressions. I mean, if you're given a terminal symbol set sigma, you know, of characters, some character symbols, you can form regular expression by concatenation, by closure, and all of that. So every token class that when we study the language, we study them as English description, is actually encoded in terms of regular expression, and that actually is the starting point. So you say that you have the regular expression of different token class, and you let the input program from the current position of the character pass through these regular expressions. Now, certainly, one of the regular expressions will match the stream of characters that you are feeding into it. The one that matches first, you declare that to be the current token. And then you restart the whole process and start matching again. We will see more of that, but I'm just giving you the broad overview. So you have the regular expression for every token class. So what you need is you need a recognizer to be built for each and every regular expression which correspond to different token classes. So how do you build a recognizer for a regular expression? That is a part of the process which you have dealt very well in terms of the flat course. So you know that the regular expression can be converted very easily using certain basic rules to a non-deterministic finite automaton, or NFA. Then we know that every NFA can be converted to a DFA and optimized whatever deterministic finite automaton, so that it can be written down as a. This is a basic theory of finite automaton that you must have studied. And finally, in the DFA, whenever you reach a final state of the DFA, wherein you say that you have found the lexem of the corresponding token class, then you take some actions for lexical purposes. Like you announce that token, you keep the lexem information of that token if required in certain data structure, particularly symbol table. And then final action is to restart the whole process, the whole recognizer, so that you can proceed from the point up to which you have seen the character in the input and try to build the next token for the next token class. So this is the overall algorithm. Let me just take a very simple rudimentary example. I'll not go very deep because you all are pretty aware of this. So I'm talking about a very hypothetical language, which is kind of abstract. There is where you have two keywords, float and for, and you have identifiers which start with an alpha and continues with 0 or more alpha and digit. And here I show an NFA for a part of this lexical specification, wherein I try to look for either the keyword float or the keyword for or any identifier that is starting with float or for. I'm not looking for identifiers in general, as you can see. So what I do, I start, this is my start state shown by the arrow. So this is my NFA I'm building. So if my first, if I look at the first character, if it is F, it is F for either of the keywords. So if it is F of float, I tend to take this path. If it is F of for, I tend to take this path. And then I just keep on going F, L, O, A, T, all of these like this, so that I get this keyword float. Similarly, I go along this for my keyword for. Now, when I reach float, how do I know whether I have actually got the keyword, or actually I am at the beginning of some identifiers? For example, there could be identifier float 1. So in that case, after float, I will get a 1, which is a digit, so that FLOAT matches A to Z part of it, and 1 matches this R. So kind of we are saying is, we keep on following this, and if after float we get something other than alpha or digit, I have got the keyword FLT. Similarly for, after FOR, if I have got anything other than alpha or digit, I have got the keyword for. Otherwise, I have again another state machine which actually keeps on consuming the alpha and the digits, and whenever it gets something other than alpha or digit, it produces an identifier. Of course, this is not a complete specification. For example, if you have, I said that this is for keyword float, keyword for, and identifiers that start with float or for. So for that matter, if I have an identifier FL1, then this state machine, this NFA, will fail to recognize it, because you'll have F, you'll have L, and then on this state, you will not have a transition, because there is no transition on 1. So it should have been that since I've got FL1, I should actually jump onto the state wherein I know that it is actually an identifier, and then proceed with the identifier rule. Similarly, if I had F1, I will do that. If I had, say, Fx, then I'll have F, and then I have X, so I also jump over. So all of these, jungle of transitions will get added if you have to accept any identifier. But I'm just trying to show how the basic structure of the thing is, in terms of if I have to recognize the keyword float or the keyword for, or any identifier that starts with the part of the word float or the word for. And accordingly, I get three different final states in this NFA, which is FLT for float keyword, which is um, FOR for the for keyword, and ID for the remaining identifiers. Now, naturally, this is one which is a non-deterministic one, because in the first start state itself, you have a non-determinism of whether you on F, whether you go on the upper line or you go on the lower line. But you can very easily make that into a DFA, in this case by observation itself, because all that you need to do is delay the decision of this branching till you get the character which is next to F. So you, in the next slide, you move on to the DFA where you have F, you go to another, and then based on L or O, you go to the next. So this is the basic idea of the specification getting into the state machine. And after you have recognized any of the lexical tokens here as to whether it is FLT, then you know that the lexem is FLOAT. This other that you have seen is something other than alpha or digit, is not a part of this lexem, because that is what terminates a lexem. In all likelihood, this possibly is a what it could be. It could be a space. It could be some semicolon or something else, whatever is not character or not alpha or digit. So once you have got this, then you know that the lexem is FLOAT, and the token that you actually return is the FLT. You have found the keyword. Similarly for. Whereas when you have got an identifier, then naturally from the state machine, immediately you are not being able to say as to what that whole lexem is, because the lexem could have been 4, 1, 2, 3, or the lexem could be format. It is an identifier which is format, FORMAT, and then something else. So basically, as the lexical analysis process will continue, it is also the requirement that the lexical analyzer will keep track of the characters that it is getting, which is very easy to do, because as it is, the whole character stream is on a linear array. So this is the basic process that we will follow. And typically, so just to show you more examples of lexical specifications. So this is just a specification written. I'm not sure whether you did this kind of specification in flat, but there's a way to write the regular expression. So you're saying number is digits followed by opt frac, followed by opt expression. The word opt here is used just for our understanding that opt stands for optional. So this could be optional, this could be optional. So semantically, what you are trying to mean is a number is digits followed by a fractional part which may or may not be there, and an exponential part which may or may not be there. Now, what is digits? Digits is given by another regular expression. It is at least one digit followed by. So it is actually, if you think in terms of the regular expression operators, then it is a positive closure. It is digit plus, which can be written as digit followed by digit star, which is a clinic closure. So it's one or more digits. Every digit could be anything between 0 to 9, which is easy to understand. Optional fraction could be that do I have a fractional part? Yes, if I do, then I will have a dot, which is the period or decimal point in the number, followed by a digit, or I will have epsilon, which means that this is optional. So this is not going to be there. This is not. And then we have the exponential part, which is also optional. And in that it may not be there, which is epsilon, or it could be a specific symbol E followed by the number of digits, that is you're saying that what is the power to which the exponent has to be raised, and that could also be a positive exponent or a negative exponent or any positive or negative marker missing, which means positive. So much things that I have been talking is in terms of this set of regular expressions. So that kind of gives us a flavor of how our integer floating point constants can be described in terms of regular expression, taking from the English language specification that we have learned from them. Though in reality, things have happened the other way. People have first formalized the regular expression and then written the English language description for people to understand. So similar thing is given here for the character class, which basically are identifiers. So any identifier is letter followed by sequence of letters and digit. Here is any letter, here is digit, and so on. So given this, naturally, if I look at a floating point or integer or floating point constant in terms of the specification that we have talked of here, you can say something similar. You can have a digit followed by digits and then the exponential part. Or you could just have no digit, just starting with the dot. Those kind of, you have a digit followed by digits, followed by the period, then the exponential part. All of these different things that may come from your regular expressions describing the integer and floating point constant get expressed in terms of an NFA, which you take to DFA, and finally the recognize. So that, this kind of becomes a standard, very standard process. So before I go into the representation of the tokens, let me at this point just stop for a while and get back to see if you have any questions. So I would ask here if anybody has any question or observations or anything. I'm sure this is quite. You must be finding this quite elementary, because most of it is actually what you have done in flat. It's just that we are using those algorithms in terms of our requirement of a lexical analysis specification.
There doesn't seem to be any questions at this point.
No question at this point. Okay, we'll go down. We haven't done much. Okay, so let me go back. Okay, so I'm back to now. So the point is whether, when you have this kind of a state machine internally built and made into a DFA, you will have final states which tell you that you have got a token. Right? You have got a token which is which either is a identifier or it's a constant or all of the different things. So now you will have to, in the output of the lexical analyzer, as the input is the sequence of characters, output is a sequence of tokens. So the tokens will have to be outputted. Now, in terms of outputting the token, you need a representation for the token. So tokens in general are represented by a doublet, a pair. A token is typically taken as a pair, in which the first part of the pair is called the token class or the token name. That is, variety of tokens belong to the same category. Like everything that that is a name is an identifier. All kinds of numbers, integer numbers, are numbers by themselves, and so on. On the other hand, there are certain token classes. So kind of here you have a token name or a token class which is ID, identifier, or number generated. There could be, and then a particular identifier could actually have a very different, will have a lexem, like we saw in the earlier discussion. We had lexems for Fahrenheit, for centigrade, and all of that. So it has a lexem which is a one or more characters long as to what has been extracted to be the character string that corresponds to this particular token. Right? So you have a, a token class, which is the token name. And then you have a second component, which you say is the attribute value. That attribute value tells you what is that token details. What is that token specifically. So if we look into this, we'll see that there are tokens. I mean, there are different possibilities. One is there are tokens like if, then, else, this kind of, which are keywords, where every token class has only one token. There's only one if. So if followed by anything which is not a character or digit is not an identifier. It's a keyword if. And you don't need an attribute for that, because that's the token class itself has only one member. So those are classes. Keywords typically fall in this. But those are classes where you do not have an attribute value to describe anything further, because knowing the class is knowing the token. Whereas there are classes like operators. So you're saying that these are all operators which belong to the same token class called relop. Relop is relational operator. But in specificity, each one of them could be a different operator. So less than is a relational operator, as well as less than equal to, so is equal to, and so on. So it is important to know that it is a relational operator as a token class, but the specific token, which particular relational operator it is, comes as an attribute. Similarly, I could have arithmetic operator, addition, multiplication, subtraction, division. I could have unary operators and so on. Now you may question as to, could we not take any of the two extremes? For example, one extreme could be that we call all of them as operators and put the specific attribute value to distinguish a less than from an addition. Yes, we can do that. The reason we will not do that is the fact that certain groups of operators can occur in certain contexts and behave commonly in a certain way. For example, if I have a relational operator, what are the things I know? There's one thing I know, it's a binary operator. Right? That's one. Then I know that a relational operator will take two numerical values in usuality. It will take two numerical values and will produce a Boolean value. A less than B. A is a numerical value, B is another numerical value. A less than B is true or false. So all of these six operators behave in the same way, and that behavior is different from the way the binary addition operator works, which takes two values, produces a value. Multiplication takes two values, produces a value. Subtraction takes two values, produces a value. So we might want to group them differently, because as a group, they will have different role in the context of the syntax and semantics that we will try to put on them. Similarly, a unary operator may, it looks plus, but 3 plus 5 and plus 7, in both of these, they are different operators. 3 plus 7 is an addition binary operator, so should belong to the token class binary operator. Plus 7, on the contrary, is a unary operator, which should belong to a different class. How lexical analyzer will figure out, because certainly the moment you hear this, you can understand that there are cases where just the characters in the token may not be able to tell you what that token should be, because the characters in the token in both cases is plus. But in one, the context of 3 plus 7 tells you that it is a binary addition, whereas if I say x assigned plus 7, I know that that plus is a unary operator. That's kind of. So it does not make much sense to treat all operators in the same token group. Rather, we will have certain subgroups like relational operator, like unary operator, like Boolean operator like and or not, uh, and then have specific attribute values to distinguish the specific operator. Now, the other extreme also, for the same reason, the other extreme of representation also does not work, where like keyword, if we want to make every operator a separate token class. So I'll say that I have a token class LT, I have a token class LE, I have a token class EQ, each one of them having only one operator member. Again, that approach also does not work because then I lose the information that 6 of these relational operators are kind of can appear in the same context, right? So there's a lot of value in terms of this representation where just a token class or token name could tell me what that token is, or I would need the token class token name and an attribute value. The token class tells me the category to which the token belongs, and that attribute value tells me the specific token that actually has happened. Now, when you come to the case of identifier, you come to something more interesting, is that when an identifier is a token class, the actual lexem, actual name could be Fahrenheit, could be centigrade, could be X, could be velocity, could be fraction, anything. So the fact that it is a token name which is identified does not tell you the details about this particular identifier, which is the first important details is how do you identify it? You know it is an identifier, but subsequently you will need to relate between 2 instances of Fahrenheit or 2 instances of centigrade in the same program to be the same variable. So just knowing them to be identified does not help. So you need to have that string, lexem string along with it. So you could have put the attribute value as a lexem string here. But what we do something smarter or something more advanced, as we'll get to see, is we start putting these in a table called the symbol table. And we just put a pointer to the symbol table record. So for every identifier, we create a record. A field of that record is the lexem, which is this word Fahrenheit, the word centigrade. But there will be several other fields. And as we will see, that this is just the beginning of this symbol table record for an identifier that starts getting created. And there'll be more and more fields which will get populated over time. For example, the very important field that we will need to get populated is the type of the identifier. Is it an int identifier or it's a double identifier and so on. And that all those will come. So you need a more rich information for these token classes, which are either identifiers or number literals. You will need similar information for strings and so on. So your attribute values in those cases are actually records which are put in corresponding symbol table, and you put a pointer to that. So we have seen 3 categories of representation. One where just the name is enough, only one member in every class. One where there are classes of predefined fixed set of members, so that you have the token class as well as the attribute values to describe each member. And then the open classes where you have the token class and a open descriptor for that class. And there are few tokens or lexems for which you have nothing, because they are in the program just to facilitate the human understanding or the lexical analysis process. So things like blank or space, in many cases, have no role in the final program. But if we wrote everything in the program without any blank, then we will find it extremely difficult to read. Or for that matter, say new line. In C program, C++ program, most of the programming languages, most, not all, like it does matter in say Python as to whether you put the new line or you don't. It does matter in Python as to whether you put a tab or not. So it specifications vary. It is not a white space. Your space or tab or new line is not a white space, ignorable token entity in Python, but it is ignorable in C or C++. So you can put tab to create nice indentation. You put new line to put different statements on line so that you can read it. You put spaces in several parts of the program to make it readable and so on. But in terms of the token, lexical token output, these have no value because they do not represent anything in the program. So these are called white spaces so that they can be ignored. So their representation is nothing. Whenever you come across a series of spaces, you just ignore them. You don't output anything. No token name, neither token value. So you just keep on consuming. We say we keep on consuming. The same thing will actually happen for cases like comment and so on. So this is a basic token representation that you get into. So with that, this is just a another example of an FSM for relational or logical operators. So we know we have 6 of them. So you start here. Of course, it's a part of a much bigger machine because you didn't know that only the operator will happen. But certainly somewhere in your big state machine of all kinds of token classes, this will also feature where if you have a less than, you go here. It's followed by equal to. You have a less than equal to. So you identify and return rel op ali. So what you are saying that I have found a token of relational operator class, and the specific attribute for that is less equal to le. Whereas I have a less, and then I have nothing, epsilon, then I return. So what does epsilon mean here? Epsilon mean here is you have something which is other than what can come after less than, right? So for example, in some languages say less than greater than is not equal. So if that is there, then this is not a greater than. But it is something which is not an equal to symbol, so something else. So I know that less than ends in less than itself. So I say this is in state 3, I have found a relational operator again with the specific attribute value LT. Similarly, I have not equal to, I have equal to, I have greater than equal to, and finally I have greater than. So this is how different, state machines, parts of the state machines can get generated, created, and this is how you actually output the different tokens from them. Okay, so that's kind of okay. Let me again stop once more just to recheck because I'll now move into the discussion of the generator, lexical analyzer generator. So let me just check on if somebody has a question. I think some questions. So I will take them one by one. I'll keep on reading them out. So Rashil had a question, sir. What does pointer to ST mean? ST stands for symbol table. So symbol table is a list of records where every record corresponds to a symbol. So I mean, to start with, symbol table could be of different types of symbols, but to start with, let us take that the symbol table is a list of all identifiers that you have in the program, where every identifier has a record for itself, having multiple fields. We will soon show you the structure. You'll have to just have a little bit of patience because we'll have to go a little bit more before we can show that. But it is a table of symbols one by one. So every record there represents an identifier. So wherein you keep the, say, the lexem of the identifier at the lexical analysis time. So Fahrenheit will have a pointer to a record in this symbol table where this whole string Fahrenheit is written as a part of the record. But it will have several other fields like type, like offset. We will come to all of that. So that is a symbol table pointer. The actual string, as ISG mentioned here in the chat subsequently, that the actual string is stored in the symbol table. That's what that actual string is. What I'm referring to as lexem. That's a formal term. Data structure used in symbol table. We will have a very detailed discussion on symbol table. We'll talk about all of that. Naturally, symbol table needs a very fast lookup because you can understand that a particular identifier will occur at various places in the program. So whenever we come across an identifier in the lexical analyzer, we have to make a decision as to whether we have already seen it in the symbol table or not. The first time a record has to get created in the symbol table. And subsequently, we will need to find out whether such a record exists. So the significant operation in the symbol table turns out to be search or find. So what is the efficient data structure for a flexible kind of search find? So anything that fits into that definition of providing you very efficient search mechanism as a data structure fits in as a data structure for symbol table. So naturally, the most typical use involve kind of variants of binary search trees, balanced, red, black, or it could be certain forms of hashed data structure also, hashing also. Now it depends on different choices, but it's a data structure which must have a very efficient search because that is what we will need to do every time we come across an identifier and find out whether that identifier already exists in the symbol table or it's coming in for the first time. And we'll see on the subsequent steps also what the reason that it will need to be searched very, very often. So Shubham, that much is what I'll answer right now. I will. It is in reality it is quite a bit more complex than what I have just said, but at the base of it, it's a search data structure. It's followed by a question from Patel asking whether it's stack or heap. It is neither stack nor a heap. As I said, it's a binary search data structure. But the interesting thing that we will see is it actually is not a single data structure. We will not have one symbol table. We'll have in a program, we'll have several symbol tables. For example, every function will have a separate symbol table. Every block in a function may have a separate symbol table, and so on. And therefore, we'll see that the final data structure of a symbol table is not one table, but it turns out to be a stack of tables. But that stack again is dynamic. It's somewhat more complex. So, I'm not giving a very flat answer, yes, no to this, but base of it is a search data structure, and rest of it will do when it comes to it. This will be covered significantly in module 5 when we talk about the intermediate code generation. Till that time, we'll take it as a flat table which can be used to keep the record information of any symbol, and we have a pointer. Well, then, Shomnath Jana, are attribute values for all lexems stored in the symbol table. So, symbol table, as the name suggests, is not for every token. It's for the tokens which are symbols. So, it's for identifiers. It could be for numbers like integer constant, floating point constant, strings, and so on. These are all the symbols. Anything else, like your relational operator, does not need the lexems to be stored because knowing the operator, you know what the lexem is. So you don't have to. So lexems are stored as attribute values in symbol table, provided it is a symbol, which means it is something which the user has defined. Whether it is an integer constant, it's your floating point constant, or it's an identifier, any of that. So, and the character string, as Professor ISG has explained here. You need first search pointed directly. Any other question? Doesn't seem like okay. This has mostly been addressed. So let me go back and in the remaining time give you a first overview of the flex process. Okay, so this is the kind of lexical analyzer program that we need to create, to generate. Let me explain what is the basic process of this generation. So, as I said, we will write the specification in terms of the flex language. It is Originally, the language was called Lex, quite obviously taken from the lexical analysis word, lexicon word, Lex language. Subsequently, lot of engineering went into it, and at a certain point, it was made significantly faster. So it was started being called fast Lex, and that became Flex. So Flex, as the name may suggest, is not derived from the word flexible. It's fast Lex is what. So you take that lexical specification, which is kind of a program. It's actually a set of regular expressions written in the form of a programming language. And then you pass it through a compiler, which is called the Lex compiler, which translates the lexical analyzers into a DFA, the translator. So regular expression to NFA to DFA. So what is a DFA? DFA is represented in terms of states and transitions of states. So DFA is necessarily the transition table. And then you need actions for that. So the transition table could say that on this input you transition to this, or on this input you already are in the final state. So you have to take some action, where the action typically is to spit out the corresponding token with the lexem and so on, and then go back and start working it. So this is the basic lexical generator. Along with that, you need a driver which will actually apply this lexical analyzer on the input. So this just generates the DFA, but this is a static thing. So you have something. There has to be a driver, which is now here called the automaton simulator, which is simulating that deterministic finite automaton according to the transition table, and which has pointers on this is the input buffer of the program. From left to right it's going, and this is the point where you started processing. Lexem begin is the point where you started processing the current lexem after finding the last token. You keep on doing that, keep on going forward to the right based on the actions from the transition table till you come to a final state in the DFA, and you know that you have to output the next token. So what comes in between is the lexem, and you spit that out along with the lexical class and all the details, and then you reset your lexem begin to the new point and start again. You keep on doing that till you exhaust the input buffer. So that's a simple, very simple scanning process. So in this process, you are necessarily making a scan of the input from left to right. So a wide part of the community also refers to lexical analyzers as scanners, because it scans the input and produces the tokens, produces the lexical token. So that's a basic over. So the key thing is this part of how do you write the lexical specification and what does the lexical compiler do. Okay. So for understanding this flex specification, this is a very simple block with declaration and some simple expression and assignment. So this block has two special symbols, curly braces, to make it into a block. There are keywords int, there are identifiers x, y, as you can see. There are operators plus, star, assignment. There are special symbols, semicolon, and there are of course a whole lot of white spaces, the space here, space here, space here. And as you can see that the space here is necessary, because without that int will not remain a keyword, whereas the space here between x and equal to assignment symbol or assignment symbol and 2 are optional. I could have removed them. And I have a whole lot of, probably I have tabs here, I have new line here. So this is all that this my simple input example contain, and I'll keep on using it through the specification to show what kind of tokens finally get generated. But this is a very small subset of the variety of tokens that exist, but kind of a wider subset. It also has integer constants, this specification, this sample. Now, I'll just give a quick overview of the flex language or flex specification, as we say. A flex specification is a specification program which has three parts. There is a declaration section, there is a translation section, translation rule section, and there are auxiliary function section. And these sections are separated by percentage in a line occurring at the beginning. So these are the three separators. So these are the three blocks. So here is an example. So that let me take a little bit of time to explain this. So as you can see here, percentage, here percentage. So you know from the beginning to this part, percentage is a declaration. From this double percentage to this double percentage, the middle part is the translation. And the remaining part is the auxiliary. So these are the three. Now what comes in the declaration? The declaration part again has two things. One are which occur between this pair of symbol, percentage opening curly brace, percentage closing curly brace, between which you write C declarations and definitions. You write pure C code. And whenever I say C, I also mean C++. Flex can generate C as well as it can generate C++. So you could write C, you could write C++. Every time I will not keep on saying C, C++, C, C++ like that. I'll say C. Understand that both these languages could be used. But this is a pure C code here. Why do we have that? Because this whole specification, when we compile by the Flex compiler, then what gets generated is a C program. So that C program will need declarations for itself, will need definitions for itself, which are typically at the beginning of the program. So those parts will be put in here. We'll come to more detailed example, don't worry. I'm just now trying to give you the sense of the structure. The second part in the declaration section is a definition of different regular expression. I have already shown you that there are different regular expressions. So every regular expression has an expression. Now what we do instead of, since the regular expressions can be complex, more and more complex, and extremely complex. So we give a name. You can give any name to a regular expression. So here is saying int. There's a tab here, which is a syntax mandatory. Int tab. Then you put in double quotes int. If you put something in int in double quotes, it means that exactly that sequence of characters has to happen to define this regular expression. So naturally, you can see that this is something which will be used for all kinds of your keywords, which are fixed strings. Then you have the regular expression for ID, which you write like this, where these are some of the Lex symbols for writing regular expression, like your square bracket means range of character sets with the dash. So within square bracket, A dash Z means A, B, C, D up to Z. Putting characters side by side are just, so this defines a set basically. Then a star after such an entity, after a regular expression will mean clean a closure. A plus will mean a positive closure. So ID necessarily says alpha followed by alpha or digit, any number of. Then we are saying that punctuation, punct is punctuation or delimiter, where we have put a character set which is just containing a semicolon. I can put number of them, but I'm just writing it for the specific, for a very small example right now. Then I say constants. Constants are meant for your integer constants for that matter. I say 0 through 9 plus. So you can see that this regular expression specification will give you something which is not very, very common. For example, you can write a constant which is 0, 0, 1, 2. Right? That's not a typical way you will write, but Since this gives you 0 through 9 plus, you can write 0, 0, 1, 2, which is a constant. Then I have a white space, which is a collection of 3 characters, space, tab, and new line. So in this way, I can write a whole lot of different regular expressions and can give names to them. Then comes the next section, which is rules, wherein on the left, I have a regular expression. And after a tab, within curly brace, I have a C code, which is the action that would be taken when the state machine reaches the final state of having accepted that regular expression. So this says within curly brace int means I'm using the regular definition int, and if I have found an int, that is if I have found the string and I come to the final state, then this is the action that I take, which is my rule. Similarly, if I found an ID, this is the action that I take. Similarly, I can use the regular definitions that I've put in here in the definition section, or I can directly write a regular expression. For example, as I've written here, I've put within double quotes, I've put the plus symbol, which means that whenever I get the plus symbol, that's a regular expression that takes me to the final state, and this is the action that I take. So these are the translation rules section. And finally, again, I have for translation, I have finally the C programs, functions, the main function of this driver, and so on that need to be given. So this is, at a nutshell, we are almost running out of time. So I will again revisit this tomorrow, but this is in a nutshell as to what the structure of a flex specification, having 3 sections: definition section, translation rule section, and the auxiliary function section. And the definition section containing C declarations and definition, and regular definitions for the specification of the language. So with this, at this point, let me stop. If there are some questions, let me take that, and then we'll continue in the next class. Are there any questions?